So let's work on this harder question, another example of using a right-hand rule. So we're going to do an example called magnetic force on a power line, and take a moment, pause the video, record, and read the question, and then we will start working on it. Okay, so we have a power line runs east-west, and the way that I want to get this up is I'll put this over here and get the document scanner over here so we can have both of these. Oh my goodness. Okay, so I've got this power line that runs east and west, and at this location, Earth's magnetic field is parallel to the ground, points north, and has a magnitude of 50 microteslas. So let's draw what that looks like. So the first way when I'm trying to draw something that I usually draw something is to draw never eat sour worms, or however it is that you like to write it. So I draw a little compass here. So I have a power line that runs east to west. So my power line runs like this. Okay. And at this location, Earth's magnetic field is parallel to the ground and points north. Okay. So I have that the Earth looks like this. All right. So the reason that I drew my lines as pointing up toward the top of the page is because north is the line that I have drawn toward in that direction. Okay. And I've drawn my wire as going east to west because we were told that this is a wire that runs east-west. And so in previous questions, we worried about this dip angle, and I didn't worry about it here. And the reason that I didn't worry about it here is because it says that it points north. Okay, we were not given a dip angle. And so if you'll recall, I have this from a previous video. We were talking about Earth's dip angle being something that points at an angle. So that would be, if there was a dip angle here, we would say that it doesn't just point north, but it also points north and down into the ground. But in this question, we don't have to worry about that because there is no down into the ground direction. It's just something that points due north. Okay. So we're fine drawing this whole problem just with the normal compass directions, and we can call up to be out of the page and down to the end of the page. Okay, so we have a 400-meter length of wire, so I will write out that L is 400 meters, and the Earth is 50 microteslas, so I'll put that as 50 to the negative 6 teslas. I've already got that converted into teslas. And the mass of this is 1,000 kilograms. I'm not quite sure how that's going to be useful yet, but I'm just going to write down all the numbers that I have. And what we want is direction and magnitude of current. So this is a little funky of a thing to ask for because usually we don't think of current as being a vector, and it's not, right? So we don't always think about current as being something that has a magnitude and a direction. But what we mean by that is the current going to be going to the east, or is the current going to be going to the west? So let's draw this. So we can think about the direction first, or we can think about the magnitude first. I'm going to think about the magnitude first, because that's an easier question for me to do. So if you can go ahead and pull out your equation sheet. If you don't have it out, pause it and go find your equation sheet and look for an equation that seems like it will be useful. And so here I am, is that I have found this right here, this equation that says FB is ILE sine of theta. Now theta is the angle between B and I, which is here 90 degrees, right? So whatever the current is, it's going to travel in this east-west direction, and B is going to travel in this north-south direction. And if you go ahead and plug sine of 90 into your calculator, you should get 1, okay? So what we are really looking for is this force, this maximum force, that is I times L times B, and we get to ignore that data. So I think maybe now would be a great time to draw a little diagram so we can visualize what's going on here. So this is all well and fine, but how are we going to get a force to levitate a wire? So let's just draw a regular old drawing. These are 2 power lines, and I have a 400-meter long length of wire spread between these 2 power lines like that. Okay, so over here would be east, over here would be west. And it'd be helpful to figure out maybe north and south, just so that we're getting a little bit better about drawing these things on the piece of paper. So let's imagine a person standing right here with her back to us. So she's looking into the page. And so if you are looking from the end of the page here, east is on your right, west is on your left. If you have a really hard time visualizing this, go ahead and stand up and do it. That's the great thing about a video, is that nobody's here to judge the way you're looking. And the thing I want you to consider is whether or not north is into the page or out of the page when you're looking here. So if you're standing with your back, so we're seeing this person's back, right? This is the back of her head. This person is looking in the direction that is north, okay? She's looking into the page, and north is the direction that is into the page. So she's looking to the north, okay? So in this diagram, north is into the page, and south is out of the page. And this must mean that up is to the top of the page, and down is to the bottom of the page, like that. Okay, so this is the same thing that we're drawing here that we drew up here, but our dimensions are a little bit differently. So here we have northeast, south, and west resolved in the plane of the page. And here we have east, west, up, and down resolved in the plane of the page. It's the same sort of a thing. But here we know that the magnetic field points to the north. So we would be able to say that B of Earth points to the north, so it would be pointing into the page. Just another way to practice visualizing how you draw this on a piece of paper. Okay, so the reason that I drew this wire here, and now my wire has gotten messed up, is let's draw a force diagram for the wire. How do we get a wire to levitate? I would argue that there are 2 forces acting on this wire. Can you argue what they must be? If we draw a force diagram for this, remember from last semester, when you're drawing a force diagram, you draw the forces acting on the particle as though all of the mass of that object is in the center of mass of the object. So we'll draw a force diagram right here in the middle of our long wire. And I drew an arrow pointing down, which is, of course, for the force of gravity. Okay, so the force of gravity points down. If this wire is going to levitate, then we must have an equal and opposite force that points up. And this force must be this magnetic force. That's the physical mechanism for how we're going to try to get this wire to levitate. So we're going to have the force of gravity that points down and a magnetic force that points up. So the magnitude of that force must be something that is equal and opposite to the weight or the force of gravity on the wire. Right? If it's a little bit less than the force of gravity, then this force will cause the wire to accelerate down. If it's a little bit more than the force of gravity, then this force would cause the wire to actually accelerate up. So this maximum force must be equal to mg. So that's a big step. Right, I substituted mg in here because I know that the force of gravity equals mg. And since these two things are equal, I must be able to plug that into there. All right, now I'm ready to solve for the magnitude of this current. Okay, so I have a current, I know M, I know G, I know the length of the wire, and I know the magnitude of the external magnetic field. That's the magnitude of Earth's magnetic field, so I can solve for it. So I'll divide both sides by LB, and that will cancel the LB here, and I can plug in that I is mg over LB. Let's plug in all the numbers. So mg is 1,000 kilograms times 9.8 meters per second squared, and divided by 400 meters times 50 times 10 to the negative 6 Tesla. And plugging in all those numbers gives me 490,000 amps is the magnitude. Okay, so now let's figure out the direction of this. We'll check sig figs to make sure. I have 2 sig figs written here. And when I go look on the computer, I see that the 50 microtesla has 2 sig figs. This one has 3. This one has 4. So we are going to go with the smallest number of sig figs, which is 2. So rounding that to 2 sig figs. And as you can see, this 490,000 amps is way smaller than a typical value. So the problem says that a typical value is about 850 amps, which makes sense. We don't typically see power lines levitating, so that's not a surprise. Now we need to figure out, we've got the magnitude, now we need to figure out the direction. So let's figure out the direction. We need to figure out how to make the magnetic force point up. Okay, so in the right-hand rule, we want our thumb, because our thumb always goes with the force, to be pointing up. Okay, so I'm going to take a minute and pause this and try to figure out what you think, and then when you unpause it, I'll show you how I do this. Okay, so I can do this with either of my diagrams. I'm going to start with this diagram here. So I'm going to use my right hand, and we'll use the right hand rule that is the one that says that for current in the direction of the force. So that is that my palm starts from my wrist and goes out to my knuckle, points in the direction of the current, and my fingers are going to turn to point in the direction of the magnetic field, and my thumb will be the direction of the magnetic force. So if I want to see what goes on, this is a very awkward angle for me. If I want to say, let's say that the current goes to the west, so I put my palm pointing in the direction to the west, and now my fingers need to curl so that they point in the direction of the Earth's magnetic field. So I'm going to rotate this like that, and now I see my palm points to the west, my fingers point east to the north, and my thumb is pointing into the page, which is down. So if the current is going to the west, then there would be a magnetic force which points down. That is not what we want, right? We don't want the magnetic force to point down. We want the magnetic force to point up. So let's try it the other way. Magnetic current going to the east, my fingers will turn to go in the direction of Earth's magnetic field, which is to the north. And now my thumb is pointing up at the camera, which is out of the page, which is our up direction. So current to the east gives a magnetic force that points up, which is what we wanted. So we must have current to the east. Oops, I'm writing, but I'm not showing you what I'm writing. So I just wrote current to east. We do the same thing here. Okay, so here I've drawn that east is this way and up is the way I want my thumb to be. And the magnetic field points into the page. So again, current is with my palm. So I'm going to put my palm pointing from wrist to knuckles to the east. I'll turn my fingers so that they point into the page. So that's like that. And the way that my thumb naturally goes is the direction of the force. My thumb is pointing up, and we wanted a magnetic force to point up, so it works either way. Okay, so let's move on to a couple more things. So this is a review problem. I've already done this problem. We did it in class, though it's been a very long time since the last class. So if released from rest, the current loop will move, and the answer to this is that it will rotate counterclockwise. So just to remind you how that works, I'm going to get another piece of paper here, and I'll draw what is there. So this is check 20.12. And we'll draw V this way. And here's my loop of wire. So current is going out of the page on the right. It's looping out or up and around and then into the page on the left. And so if B is to the right, this is that same right-hand rule that we were just using. So over here on the right-hand side, I want to put current out of the page. So I'll point it right straight up at the camera. I'm going to turn my fingers so that they point in the direction of B. So this would be a good thing to do on your own before you watch the answer. I'll turn my fingers in the direction of B so that they go like that. And now my thumb points up, and that must be the direction of the force on this current here. Over here on the other side, I have now current going into the page. So I'm going to put my fingers pointing into the page. I'll turn my fingers, my palm is into the page, my fingers point in the direction of B, and now my thumb points down, which is the direction of the force. Okay, so that is what that looks like. And this is actually the basis for tons and tons and tons of practical things. If you've ever heard of a motor, right? How do you get something spinning? This is how you get something spinning. You have a current and a wire in the presence of an external magnetic field. So we said that this will experience a torque, but no net force. And so what I mean by that is that there is no net force on this, right? There is an equal and opposite force pointing up and pointing down. So this won't translate. It won't move up, down, left, or right. But it will experience a torque. So if you remember from the first semester, a torque is a force that acts to cause a rotation and not a translation. So this thing will spin. So anything that will spin is something that is experiencing a torque. Or at least something that will change its rotation is something that will experience a torque. So galvanometers. This is a perfect example of a galvanometer. So let's show you one that I've been using in class, which is this one right here. So this is a galvanometer, and the way that this galvanometer works is that there's all these knobs down here. But what these knobs really do, and you see I actually have two of them connected, a wire connected over here and a wire connected over here. So if you put input into these two knobs, if they send a current through a wire, right up in here, I'm not sure if you can see it, but there is actually a coil of wire right there. So that coil of wire is surrounded by a magnet. So there's magnets on the outside of that coil of wire. And if there is a current going through that wire, they will experience a force and it will cause this dial to change. So I have a battery here, and I'm going to go ahead and just plug in these probes, these wires that are connected to my galvanometer. And when there is a current going through this, the coil of wire experiences a force, and that causes the dial to turn. So remove the dial, there's no force. And of course, the larger the current, the more the torque will be on this coil of wire and the more the dial will move. So this here moves it, not a very well calibrated galvanometer, it's pretty old, but it moved to the 1 when I had my 3 batteries. So that was 4.5 volts or so of voltage. If I only do 1.5 volt of voltage, you see that it moved less. So 3 times as much current is 3 times as much magnetic force, just like we saw from the equation that we just used. We have a pretty, so this is how a motor in your car works. So what goes on inside your car is there's a current inside a magnetic field and it causes something to spin. If the thing that's spinning is, say, connected to a wheel, then now you have spinning wheels in your car. We have a pretty big claim to fame here in Albany. Joseph Henry was a poor immigrant who lived in Albany, and I can never remember, I think maybe he was Irish, Scottish, one of those two. He created the very first motor here in Albany. Actually, he created it at the Albany Academies, which is only about a quarter of a mile away from the Sage College of Albany campus. So that is our claim to fame. And actually, Joseph Henry was also the first ever curator of the Smithsonian Institution. So if you go down to the Smithsonian museums down in Washington, D.C., you'll actually see his name on a plaque outside of the Red Castle, the main Smithsonian building, because he actually lived in the Red Castle. He was the first person to ever live there. And this is also something about how MRIs work. So the way that MRIs work is that inside the atoms in your body, you can think of them as being like little compasses that will line up with the North Pole, lining up with the direction of the magnetic field, like is drawn here. But you're actually, the magnetic moments of different atoms can also line up exactly wrong, like it is here. So most of the time, everything lines up like it should be, but you can almost think about this as being like an unstable equilibrium. Like if you are just right, then you could balance a pen straight on its tip if you did everything just right. There's like this unstable equilibrium where it can be happy there. And as this magnetic moment between your flips, there's an energy difference that occurs here. And so the way that an MRI works is that it sends out a probe field specially tuned to the different magnetic moments of different atoms that might be inside your body. And the way that those energies are sent is lets you make a map of exactly where different types of tissue are in your body. And I actually have a little simulation here that I wanted to show for how that works. So this is a PhET simulation, which is the kind of simulation that you will be using in your labs. But we were not going to use a PhET simulation on this lab. So what's shown here is nuclear magnetic resonance. So this is the basis for how an MRI works. So you can see that inside the MRI is basically a giant solenoid. So there's some solenoid coils on this side and some solenoid coils on this side, and the person inside the MRI would be this way. So if we have photons, little particles of energy that are the energy transmitters that are sending energy through the MRI. And now you have all these different atoms inside your body that have different magnetic moments. If the photon hits just right, then it'll flip the magnetic moment of that thing. And so that's how an MRI works. And you can this is pretty much the same thing, only a little more realistic thing. So in a real MRI, there would be a detector over here. And what's going on is that as different probe fields are sent through this person's, I guess we're taking an MRI of their brain, when the magnetic moment gets flipped, it will send a little bit of energy to a detector, and the detector can see where it is in your head based on sort of where it lands on you. So if I say at a tumor, now if we're looking for where the location of a tumor is, you see that there's all of these different things here that are now shooting toward the detector. And if you've ever been inside an MRI, then you know that there's all these really loud noises, and they make weird patterns. So you'll kind of be sitting there for a while, and it'll be like doom, 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 and then a little while later, like that sound is the sound of the current going back and forth really quickly, the sound of the current changing direction. And so I wanted to show you what that is. I have this sort of specially set up to a frequency here that is really interacting a lot with this tumor. But at other frequencies, there's less interaction with the tumor, okay? And so they call this a probe field, where you can change the type of energy, the frequency of the energy that's being transmitted through your head, and that has different interactions with different types of tissue. And so depending on the type of interaction that happens, you can infer things about what type of tissue is where. Is that a water-dominated tissue? Is it this kind of tissue? Is it that kind of tissue? Is it bone tissue? Is it bone tissue? I don't think you'd call it bone tissue. Is that just bone, or is that tumor, or anything like that? Okay. So this is what a probe field looks like. So it's flipping the atom dipoles from the high energy state to the low energy state in an MRI. And that is how we get maps of what goes on in your brain. And the awesome thing about an MRI is that it's totally non-invasive. If you ever in the hospital and you have a choice between getting a CT scan and getting an MRI, I hope that they will be advising you to take the MRI, but if they're not, you should strongly be advocating for having the MRI done first, because there's no radiation, there's nothing harmful going through your body, it's just using a magnetic field to interact with your body a little bit, which is a way less invasive thing to do. Now, if you've ever had an MRI done with contrast, which most of the time I think they tend to do MRIs with contrast. That contrast dye is radioactive, so it's not a totally harmless procedure. But in general, unless you have steel in your body somewhere, something magnetic in your body somewhere, an MRI is one of the least invasive things that you can have done if you need real imaging. Okay, I think I'm going to stop here and we'll do the next video.